My name is Grigory Lihachev. I'm a postdoc in the Laboratory of Photonics and Quantum Measurement at EPFL, and I'm here to present our latest result on low noise frequency-agile hybrid integrated lasers for the LiDAR. This work is done in collaboration with Sunil Bhav group in Purdue University. So low phase noise are important for in a wide range of technological and scientific applications, such as distributed fiber sensing, coherent LiDAR, and coherent telecommunication. In some of these applications, frequency tunability is often a further essential requirement, for example, to lock lasers to stable references. So over the past decade, the development of heterogeneously integrated lasers has led to a new class of CMOS-compatible, highly integrated lasers. And the chart compares the intrinsic line width for several recent demonstrations based on DFB, DBR, and external cavity configurations. Today, the lowest phase noise of compact semiconductor laser was achieved by self-injection locking with discrete crystalline resonators that have very limited frequency agility. The main difficulty in achieving high frequency agility lies in the rapid tuning of the photonic resonator that provides line width narrowing while maintaining a long photon time in the same resonator. This chart schematically shows the progress made in reducing the intrinsic laser line width on the horizontal axis, also comparing the available tuning speed, vertical axis, for different types of integrated lasers. In our work, by using self-injection locking of indium phosphide laser to a microresonator, monolithically integrated with aluminum nitride MEMS-based actuators, we achieve both frequency agility and intrinsic line width of 25 Hz. In our approach, we use a silicon nitride platform for passive photonic circuits. Silicon nitride is CMOS compatible, has a large bandgap, wide transparency window, high kernel linearity, and weak Raman and Boolean gains. Histogram of intrinsic cavity line width for microresonator with 10 GHz FSI used in our work reveals 9 MHz as a most probable line width. EPFL has significantly developed the fabrication process for silicon nitride, enabling wafer scale fabrication of millimeter large resonators with high quality factor and high yield. And silicon nitride integrated circuits are fabricated using the Damascene process, followed by the monolithic integration of aluminum nitride actuators. The piezoelectric aluminum nitride thin film in green is sandwiched between the top aluminum and bottom molybdenum electrodes. And upon voltage driving on the electrodes, bulk acoustic waves are formed vertically in the substrate, called H-bar mode, beneath the actuator. The silicon nitride waveguide in blue is fully buried in the thick silica cladding to preserve the optical losses. And piezo actuator allows to tune the cavity resonance and features excellent linearity, low hysteresis, and low power consumption due to a pure capacitive nature. So the laser self-injection locking is a phenomenon of laser line width narrowing via external cavity feedback. It has been first proposed and studied more than 30 years ago on the microscopic reference cavity, and in our scheme, light emitted from a single frequency laser diode is coupled into the microresonator via bus waveguide, and a small portion of light is reflected into the counterpropagating mode due to the relay scattering on the surface of volume inhomogeneities and is directed back to the laser. Due to the high Q of the resonance, such narrow band light beam forces the laser to oscillate at the cavity resonance frequency, which we can tune by applying voltage to the integrated actuator. On the left, you can see a photo of our experimental setup and the optical spectrum of the laser emission and the frequency tuning curve of the self-injection locked laser in the linear regime. One of the key parameters which we can control is the feedback phase, in our case controlled by a distance between a laser and microresonator or by integrated phase shifters. Since the line width narrowing factor is quadratically proportional to the quality factor of the microresonator, the high Q of the silicon nitride can significantly reduce laser noise. And the plot shows the frequency noise spectrum of free-running DFB in gray, self-injection locked to the microresonators with a FSI of 190 GHz green, 10 red, and 2 GHz blue. In general, noise suppression is more than 40 dB across the entire spectrum, and the optical cross-correlation technique confirms that 2 GHz device produces the white noise floor of 8 hertz squared per hertz. At mid-range offsets from 5 to 100 kilohertz, the performance is limited by the fundamental thermorefractive noise of the silicon nitride MAC resonator, and analytical estimation is marked with the colored dashed lines. We could further improve it by using the resonators with the resonator with a larger optical mode volume. We observe 2 peaks in blue trace at 1.5 and due to the technical noise in our lab, and at 4.5 kilohertz due to the excitation of first mechanical mode of our photonic chip. We compare the laser frequency noise to commercially available lasers, and this frequency noise plot reveals that our hybrid integrated lasers is better than ACDL at all offsets and on par with commercial fiber laser at offset frequency range of 1 to 50 kilohertz. But now we also have a new capability of fast tuning. And the left panel demonstrates a typical frequency tuning spectrogram obtained by heterodyne bit with a reference laser, showing frequency change upon the linear tuning of the diode current. And dashed areas correspond to the range where the laser is self-injection locked over 2 gigahertz. The panels in the middle give a schematic of laser tuning, and different voltage levels applied to the figure to the piezo actuator correspond to different resonance frequencies, and thus leading to the different frequencies of the laser. And by applying the triangular voltage to aluminum nitride, we transduce the cavity resonance shift to the triangular laser frequency change while operating in the locking range, inside the locking range. And on the right is a spectrogram of a laser frequency tuning upon the linear tuning of the aluminum nitride. Dashed areas corresponds again to the range where the laser is locked to the shifting resonance for 2.1 gigahertz, and the B current is fixed in this case. To achieve optimal tuning performance at high tuning rates, a flattened actuation transfer function is desired. So we measure a laser response to actuation using VNA, as shown in the schematic in the bottom. It means voltage on the actuator to frequency to optical frequency transduction. As shown in the plot of mechanical to optical response, the aluminum nitride actuator excites many modes of the photonic chip. They are marked in gray, leading to a non-flat actuation response. And by using an active cancellation scheme with the 2 anti-phase actuators in green, or by using chip apatization in blue, we demonstrate suppression of mechanical modes of our photonic chip. In this way, both flexural and the bulk mechanical modes of the chip are damped up to the first H-bar mode at 17 megahertz, resulting in a very flat actuation response, for example, in blue. So we next demonstrate frequency agility of our laser. We carry out a frequency modulation of the self-injection locked laser by applying a triangle voltage to the piezo actuator. Here, laser frequency spectrograms and the corresponding nonlinearities are presented for ramp frequencies of 1 to 800 kilohertz. Root mean square nonlinearity is as low as 0.5% for 10 kilohertz, which only degrades slightly at 800 kilohertz tuning rate. On the right is a plot where, with normalized transduction, comparing the actual detection frequency at odd harmonics as a function of time with a perfect triangular chop. Together with more than 1 gigahertz tuning range, such high actuation bandwidth exceeds the performance of many benchtop laser systems that rely on bulk piezo components, and making this laser source suitable for direct implementation and coherent ranging experiment. So as an actual demonstration of the potential of our laser, we perform an optical FMCW LiDAR ranging in the lab environment. And schematics of the FMCW approach is standard. By sending triangular chopped light to the target and beating with a local oscillator, we can measure both distance and velocity simultaneously. And FMCW LiDAR is immune to crosstalk, has typically higher sonar, and is eye-safe at our wavelength of choice of 1550 nanometer. On the bottom, you can see a photo of the target in our lab. It's a donut in front of a PC monitor, 10 meters away from the collimator. For the beam steering, we used a Galva scanner with 2 mirrors. We apply triangular chop with a 100 kilohertz frequency to the aluminum nitride actuator to obtain a 1.2 gigahertz optical frequency excursion of the injection locked laser, corresponding to 12.5 centimeter optical resolution in our distant measurement. To construct the point cloud from a recorded oscillogram, we first employ a short time Fourier transform with a window size equal to a half of the chopping period. An obtained time frequency plot for the target is presented at the bottom. The typical SNR for the target is more than 15 dB, and point cloud of the scene with the distant-based coloring. Donut is depicted in blue, PC monitor in green, and part of the wall in yellow is presented on the top. And the scene has been properly reconstructed using optical power from a laser in the range of 1 to 10 milliwatt. So in this demo, we can, due to the excellent linearity and narrow line width of our laser, perform ranging without any predistortion linearization. Moreover, in our approach, the DFB current was fixed, so we only sent a chopped signal to the piezo actuator. So in summary, we have demonstrated hybrid integrated laser with a frequency noise on par with a fiber laser, while exhibiting flat and high frequency actuation response. Such compact laser can be used in FMCW LiDAR or fiber sensing applications. So results from my talk are available in this archive submission. Thank you very much for your attention, and I would like to mention our collaborators from Purdue, Sunil Buff, and Hao Tian. Thank you very much.